Here in our slide number 50, we're being asked, of these compounds, one is a liquid and the others are gases. Which one and why? Of these compounds, one of these compounds is a liquid and two others are gases. Which one is a liquid and the other are gases? I got it out that time. So we're just taking a picture of a formaldehyde, C double bond O and single bond to H's. We have fluoromethane, carbon single bond hydrogens and a fluorine. And hydrogen peroxide, H2O2. What I clearly see here, again with these oxygens, I can see a hydrogen connected to an electronegative element called oxygen. We are discussing hydrogen bonds. Hydrogen has to be either attached to an O, hydrogen attached to an N, or hydrogen attached to a fluorine. The oxygen-hydrogen in formaldehyde, although they're in the same compound, they are not attached to each other, so no hydrogen bonds. And again, although we have fluorine and hydrogen within the same compound, they are not attached to each other, so no hydrogen bonds. And therefore, the only one where we have oxygen and hydrogen attached to one another and can set up the polar bonds of a hydrogen-type connection is the hydrogen peroxide. When I see that hydrogen bonds can form, they have very strong intermolecular attractions and therefore will be a liquid. The two compounds that do not have hydrogen bondings do not have strong intermolecular attractions and therefore would be labeled as gases at room temperature. And the slide is well printed over, but in the PowerPoint it's an overlay slide. You can see those words appear one at a time. Same idea here, choosing the substance in each pair that is a liquid at room temperature. It's asking me who between the two has stronger intermolecular attractions. Here I'm seeing methanol, CH3OH, where the carbon has a single bond to each of those hydrogens and then an oxygen, hydrogen. Here I have carbon attached to a carbon, giving us a structure that looks like this. Carbon single bond carbon, where the hydrogens are coming off of each carbon here, and then two fluorines here. Clearly, the hydrogen attaching back to the carbon eliminates no hydrogen bonding, and therefore will be a gas at room temperature. This compound will form hydrogen bonds and therefore will be a liquid at room temperature. Stronger intermolecular attractions when the hydrogen's attached to an electronegative element. Here's an ether, CH3O, CH2, CH3. Structural formula here shows, although the compound both contains hydrogens and oxygens, they're not bonded to one another, no hydrogen bonding. Most likely a gas at room temperature. However, here we have a carbon, CH3, carbon, CH2, another carbon, CH2, and then a nitrogen, NH2. Clearly I see a hydrogen attached to an electronegative element such as nitrogen, and hydrogen bonding can form. Therefore, this would be a liquid at room temperature. The hydrogen must be attached to either an N, an O, or an F, so that between the molecules we can set up hydrogen bonding. The attractive forces in solubility. Solubility depends in part on the attractive forces of the solute and solvent molecules. The old saying goes, like dissolve likes. Polar will dissolve with polar, nonpolar with nonpolar, but the two opposites will not dissolve. They are said to be immiscible. Liquids that do dissolve in one another are known as miscible liquids. Likes dissolve likes. Polar with polar, nonpolar with nonpolar, but not the opposite. Many molecules have both a hydrophilic and a hydrophobic part. Hydrophilic would mean water-loving, polar. Hydrophobic would mean water hating, and that would be a nonpolar end of the molecule. So solubility in water becomes a competition between the attraction of the polar groups for the water and the attraction of the nonpolar groups for their own kind. And we'll see that happen in long chains of hydrocarbons. Pentane is a nonpolar molecule. We have 5 carbons in a row. Each one of those fills out its octet with hydrogens, a molecule of pentane, C5H12. Since this is a completely nonpolar molecule, water is indeed polar. There is no attractive forces between the water and the pentane, therefore no solution forms. We literally see a layer, just like oil floating on water. Pentane would float on water, and they would not mix between them. So immiscible liquids do not form a true solution. They are not soluble. Nonpolar pentane with polar water will not form a solution. However, polar solvents with water certainly will form a solution. The polar solvent, let me get that down a little bit, that might be easier to read. The polar solvent hydrogen bonds with the water molecule. Here is a polar solvent called dichloromethane, or ethylene chloride, same idea. 2 common names for the same compound. If I place that into another polar molecule, such as water or ethanol, there are oppositely charged areas of each molecule, and a solution would indeed form based on the hydrogen bonding setting up between the molecules. With nonpolar solvents, such as hexane, toluene, carbon tetrachloride, nonpolar solvents are very good at dissolving nonpolar solutes. Likes dissolve likes. We have a 4th category of intermolecular attractions. We started with London dispersion forces, number 1. Number 2, those were called dipole-dipole attractions. Number 3, hydrogen bonding. And now the 4th intermolecular attraction is called an ion-dipole attraction. In a mixture, ions from an ionic compound, metal to nonmetal, positive to negative, cation to anion. Those compounds are attracted to the dipole of polar molecules. The strength of the ion-dipole attraction is one of the main factors that determines the solubility of an ionic compound dissolved in water. Sodium chloride is ordinary table salt. Sodium is positive, chloride is negative. When sodium chloride dissolves in water, it dissociates. It lets go of the ions, and we can clearly see the attraction between oppositely charged areas. The sodium gets aligned with the water. The chloride gets aligned with the hydrogen. The oppositely charged oxygen surrounds the sodium ion. The oppositely charged hydrogen surrounds the chloride ion. This process was what we labeled earlier as the process of hydration or solvation, dissolving an electrolyte into water. Choose the substance in each pair that is more soluble in water. Water is polar. Let's find the polar molecule. When we think of methanol, CH3OH, here is a hydrogen bond that can attract to the water molecule. This would be a hydrogen bond setup between methanol and water, a very strong intermolecular attraction. CH3CHF2 does not show hydrogen bonding. Therefore, the more soluble molecule is the one that exhibits the stronger intermolecular attraction, which would be the methanol. Here in this picture, we have a long hydrocarbon chain, 1, 2, 3, 4, 5 carbons. This is called pentane. Clearly a nonpolar long-chained carbon versus methyl chloride, CH3Cl. Clearly I see the area of polarity. More polar molecules are water soluble. The more soluble here, CH3Cl. Clearly nonpolar will not mix with water. The polar molecule will. Likes dissolve likes. So in summary, dispersion forces are the weakest of intermolecular attractions. Dispersion forces are present in all molecules. The magnitude of the dispersion forces increases with molar mass. Polar molecules